Let us talk about this problem. We are given a singly linked list. We need to print all nodes of it using recursion. We should not be using any iteration or any loop. We need to write a recursive code to print the linked list. Now please pause this video and try to write down a function that takes head of a linked list and prints content of it. For example, if we pass head of this linked list, then our recursive function should print 10, 20, 30, 40. And if we pass head of this linked list, then our recursion should print 10. And if we pass an empty linked list, then our recursion should not print anything. Let's see the recursive implementation now. So the idea is really simple. We pass head of a linked list as an argument. Like any function on the linked list, all the functions, they receive the linked list as an head. And if the head is null, it means your linked list is empty. We don't need to do anything in this case. So we simply return. And if head is not empty, then we need to print head's data. And then we need to recursively call for second node, right? So we printed the first node's data and recursively called for the second node. When you make a recursive call for the second node is going to become your new head. So it will again check if head is null. It will print the second node's content. It will call for the third node. Then third node will print third's data and will call for the fourth node. Fourth node will print the fourth node's data and then will call for the next node. So if you see this linked list example, when fourth node calls for its next is null because fourth node is last node. So when you call for null, the last call, the fifth call for the null is going to end here and it's going to give the control back to the fourth call. So fourth call, which had printed data, is now going to end because it was waiting for this to finish and this is also finished, right? And then the third call will finish, then second, then first, right? So all the recursive calls will finish once you reach the null. They'll finish one by one. First this will finish, then this, then this, then this. Let's see the working of this function step by step. We call it for the head, which is this node, right? So in Java, we pass the nodes as references, but in C++, we pass the nodes as pointers. So we pass reference of this 10. I'm using the term reference here, which is for both reference and pointers. So we pass 10 here. When we pass 10, we print 10 first, right? This line is executed, this is not null. And then we call for 20. When we call for 20, we print 20 and then we call for 30. Then we print 30 and call for 40. Print 40 and call for null. When this is called, this goes into this if condition and returns. And this gives the control back to 40's call. And for 40's call, this was the last thing, call for null. So 40's call also finishes immediately. Then 30's call also finishes immediately because call for 40 was the last thing in it. Then 20's call also finishes because 30's call was the last thing in it. Then 10's call also finishes and we get the linked list nodes in the correct order. Let's now talk about time complexity and auxiliary space for the solution. Time complexity of the solution is clearly big O of n, where n is the number of nodes in the linked list. Because for every node, we are doing constant amount of work. We are printing it and then making a recursive function call. Now, how much auxiliary space this will require? This will require big O of n auxiliary space. See, if there are n nodes, then you will have n plus 1 function calls in the function call stack at the worst case. Right? For example, you have 4 nodes and this is the point where you have 5 function calls in the function call stack, right? And function call stack storage of functions also takes space, right? So we are going to need big O of n auxiliary space in this recursive solution. That's why iterative solution is better because iterative solution requires big O of n time but does not require any auxiliary space.